So what we want to do today is the frequency response, and what we have to start is with body plot. Okay, last time we did describe the frequency response. What we mean by the frequency response, and just to make sure that we start from and we continue from last class, we say that if we have h of s, we transfer it to h of j omega, where we replace s by j omega, and this it has the magnitude of h of j omega times the phase angle of j omega, the phase angle of j omega. Okay, so what we are doing in the body plot, we are doing the magnitude versus frequency. So as you see, the magnitude A of omega will become, which is the magnitude of G of j omega. So it is a function of omega. So we plot the magnitude against omega, and the phase angle of G of j omega also will be function of omega. So we plot both versus omega. Okay, so now body plot is two plots, basically the phase and the magnitude, and for any system you have to have the phase and the magnitude. Either one alone does not mean much, so I cannot tell much about the system if I have only the magnitude alone, or so I need to go. So what we want to do today is that to continue this, and this is the second review of the frequency response, and we will focus on body plots. Okay, and body plot, he came and said, let us take the 20 log of the magnitude, and this is what it does. Basically, if you have a transfer function composed of different terms, now instead of doing multiplication and division, I do only addition and subtraction. Example, so if I have G of S, for example, equal S plus 1 over S times S plus 5 times S squared plus 3S plus 2. Okay, and I want to do the body plot. Then the body plot, you take the magnitude of this and you do the 20 log of the magnitude. So 20 log of the magnitude of G of S in this case, it is a 20 log of the magnitude of S plus 1 minus 20 log S, the magnitude of S, minus 20 log the magnitude of S plus 5, minus the magnitude, the 20 log of the magnitude S squared plus 3S plus 2. So now this, instead of doing initially we have S over S plus 1 over S plus 5 over S squared, etc. Now we are adding and subtracting. So the magnitude, if I want to talk about the magnitude, now it is the magnitude of the zeros minus the magnitude of the first pole minus the magnitude of the second pole minus, and here we took the magnitude 20 log. The 20 log. What enabled us to do this is the log, right? Is that we are taking the log. Without doing this, we cannot. That's why. That's how the log need to come into place to help us. Okay, so and therefore what we are doing, the magnitude, it is 20 log G of j omega, which is 20 log A of omega. A is the magnitude of omega as function of the frequency. Okay, and as the magnitude, if the magnitude doubles, suppose we double the magnitude, so it is the magnitude A of omega, now A, let's say call A1 of omega is 2 times A of omega. What happened to the value in decibel? The value in decibel increases by 20 dB, right? If we increase the frequency by 10, if we increase the magnitude by 10, then this will be increased by 20. If we double, it will increase by 6 dB, because this becomes, it is 20 log A of omega plus 20 log 2. What is 20 log 2? Muhammad, what is 20 log 2? 6, right? So doubling is increasing the magnitude by 6 dB. So if you double, you increase the magnitude by 6 dB. If you increase this by 10 times, you increase the magnitude by 20 dB. So this becomes really simple. So and this is explained here. Okay, now let us look at the advantage of the taking the log. So if the advantage of taking the log now, because now if I am doing the 20 log, for example, let us say that our transfer function g of s equal s. What is 20? What is the magnitude? This is 20 log omega. S equal j omega. The magnitude of j omega is what? Omega. So this is right. So 20 log omega, right? 20 log omega. And 20 log omega, it becomes a line, right? A line in what? This is a linear function in what? In log scale. Right, in log scale. And that's why the log scale, how the log scale comes in, because otherwise it is not linear. Log function itself is not linear function. But when I say that, okay, I want the log scale, I want to do it in the log scale, it becomes linear. It is now 20 times x, where x equal log omega. Right? So this becomes simple. So that's what it is now. And here I write omega, but it is actually log omega. This is and log omega. This is start with 0.1. Can we start from 0? No, right? We cannot start from 0 because 0 is 10 to minus infinity. So, right? So this is we cannot start from 0. So we start normally. For example, this transfer function where t equal, let's say t equal 1. So the corner frequency is 1. We take one decadeless. We take one decadeless. If it is 1, what is the one decadeless in the frequency? 0.1. Right? 0.1. So we start from 0.1 and we go to 1 and we take one decadeless. Now in a system that contains several poles and zeros, you might end up taking 4 decades, 5 decades, 3 decades. It depends really on the frequency of your the corner frequencies involved. Okay. So here, for example, this transfer function, I will write it here. G of s can be written as 1 over s over omega plus 1, where omega is 1 over t, right? Here omega is 1 over t, right? You know that omega, it had the units of 1 over t, right? So what would be the magnitude? The magnitude, can you tell me what is the magnitude of G in this case? Equal 1 over the square root of, let me call this omega 0. Okay, let me call this omega 0. Yeah, and this is omega 0. This is 1 over omega 0 square plus 1, right? Correct? Okay, and if I take the 20 log, so if I take 20 log G, so what would be 20 log G? It minus 10 log, right? Omega, yes, over omega 0 square plus 1. Now, what happened to the square root? Square root, it is 10, it is the 10 to the power half. Half times 20 is minus. Okay, so that's what we have. So this is what we are plotting. This is what we are plotting. Now, is this linear function in the omegas in the log scale? Is this term, for example, the second term order term, is linear in terms of the log scale? No, it is not. It is not, right? It is not. We cannot, okay, let us define log omega over x equal, omega over omega 0 equal x. Right? If you define it, you cannot split, you cannot say log omega over omega 0, okay, plus 1. You cannot say that this is log omega over omega 0 times 1 or minus 1 or so. You cannot, right? So there is a problem here. Besides, this is a second order term. Otherwise, maybe I can redefine the frequency and think of another frequency scale. Now, but look, what we can do here, what we can do now in the case when we have a 0 or a pole at the origin, so it is S or over 1 or 1 over S, we ended up with a linear function. Now here we have a pole at minus omega 0, right? Okay. Now what we do, we cannot, it's not linear, we cannot linearize, but we still can do against the frequency, we can plot it against the log of the frequency. Now this one can be thought of okay, as follows. So we can think of it at the low frequency, we take the extreme low frequency and the extreme high frequency. And so we have two frequency ranges. The low frequency range, now when it is in the low frequency compared, of course, to omega compared with omega 0 is low. For example, let omega 0 be 10 and omega is 0.1, so this is small, right? Okay. Now for this, if this is omega over omega 0 is small compared with 1, so we write if omega over omega 0 less than 1. So what is the approximation become? Minus 20 log 1. What is minus 20 log 1? 0. And so we get the low frequency limit. We call this the low frequency slope or the low frequency asymptote. The low frequency asymptote. Why asymptote? Because it is asymptotically going to 0, the frequency. So the low frequency asymptote, how we do the low frequency asymptote? If we look at the magnitude, this is the low frequency asymptote, guys. So if I look at the magnitude, this is the low frequency asymptote. It is what? A line up to the corner frequency if omega over omega 0 is 1. This is omega over omega 0. If omega over omega 0 is 1, so I can draw a line. Now the second limit, when omega over omega 0 is what? Large. When omega much greater than 1. When it is much greater than 1, what would be the approximation? Minus 20 over, okay, because the 2 now it becomes minus 20 log omega over omega 0. Linear, right? Linear by log omega over omega 0. So this is linear. Now, what would be the slope? Minus 20. Minus 20. And this where start? So this is minus 20. So if I have it here, this is a slope. So I can do a slope which is minus 20 here. And it continues. This is the high frequency slope. This is the high frequency asymptote. And this is minus 20. And this is the low frequency asymptote. So I can do it very quickly. I can even picture it in my mind. I don't need to do any calculation. I know the corner frequency, for example, is 5 omega 0 equal 5. I know what it is, right? So I don't need really to plot it. I can see it. Okay, I can see it moving in front of my eyes. Yeah.
So you said that omega over omega naught and infinity gets in the high number. How do you get this slope to minus 20?
Well, right. Okay, good. So let us see when omega. So here when we said omega over omega 0 is much less, is much smaller than 1. So this is much smaller than 1. So what would be g? What would be 20 log g? Log g in this case 0, right? Okay, now let me go to here 20 log when omega over omega 0 much greater than 1. Then this becomes 20 minus 20 log omega over omega 0, okay, because the 2 went out, okay. So this is it, right? So what is the slope now? This is minus 20, so it's minus 20x. Minus 20x. So minus 20x starts from here. The slope is minus 20. Minus 20. Why we're doing? Because we are doing omega over omega 0. So when omega over omega 0 is 1, okay, what is it? 20 log 1, 0. So it starts from here. So this is start from 1, 0, right? And it goes minus 20 when the frequency ratio is 10 times, where it goes to minus 40 when the frequency ratio is 100 times. It goes to minus 60 dB when the frequency ratio is 1000 times. So when you say 10 or 20 dB, what is the magnitude ratio? 20 dB is 10 times, right? It's 10 times more, 10 times more powerful. When we say 100 dB, it's 10 to the power 100 dB, 10 to the power 2, right? 10 to the power 2. 10 to the power 2, 100 dB. 105, 5, right? 100 dB is 10 to the power what? 5. So 5, 10 to 100,000 more. It is like the Richter scale. The Richter scale is the logarithmic scale, right? So when you say an earthquake with the strength of 5 on Richter scale, and an earthquake with a scale of 7, this means that it is two order of magnitudes more. 2 order of magnitude, 100 times more. So you see the destructive power of it, right? It's 100 times more powerful.
So you said from 1 dB to 100, 10 to the power 5?
Well, the 100 dB, it is 20 times 5, right? 20 times 5. So take the 20, bring the 5 inside, so 20 times the frequency ratio or the magnitude to the power 5, right? So this is what we are saying. The magnitude is 5 times more magnitude, okay? And if you have negative dBs, it means 5 times 5, okay, 10 to the power 5, you divide by 10 to the power 5. You don't multiply by 10 to the power 5. You attenuate by 10. Okay, now so this is now what happened when omega equal 1? When the frequency ratio equal 1, can we approximate here? How? Omega, the frequency ratio, and compare it with 1, is the same order of magnitude. So we cannot approximate. We only can approximate when the ratio compared to 1 is small. And the small, normally, it should be more than 10 order of magnitude. Or 1 order of magnitude. Yeah, so 0.1. It can be considered small. But things that are within the same order of magnitude, we cannot approximate. They are equal. We cannot now we cannot evaluate, we cannot approximate it when it is 1, so we calculate it with the formula here. When the frequency ratio is 1, we are talking about log 2.
Yeah.
So exact, we are evaluating it exact. So we got, so here this one, this is approximation. These are the asymptotes. At 1, so I can calculate at 1 log 2 times 10. What is log 2 times 10? Minus 3. Minus 3. So here I can put a point minus 3, and I can assure you, if you do a good plot, Shadi, if you do a good plot, accurate plot, I mean, you don't use any calculator, anything, just you do try to be accurate. You don't just put lines like this. You try to be accurate. So if you write with your hand a curve which comes from here smoothly, fits this point, and goes to the asymptote, you make less than 5% error without doing any calculation, and this is good enough. Okay, so this is a good enough tool. Now we go to the phase. This is the magnitude only. What about the phase? Phase angle. Phase angle. What is the phase angle in this case? Phase angle of the imaginary part. It is tan inverse of the imaginary part over the real part. And since this is a pole, the phase angle is minus tan inverse the imaginary part over the real part. What is the tan inverse the imaginary part of the real part? It is minus tan inverse omega over omega 0, right? Because the real part we made it is 1 here. So the imaginary part S equal j omega. The imaginary part is j omega over omega 0. What is the phase angle therefore for this term? Tan inverse omega over omega 0 with a minus, right? With a minus. Now tan inverse, now with omega equals 0, tan inverse 0 is what? 0. So you start here with 0. You start here with 0. Now tan inverse of 0.1, what is tan inverse of 0.1? It's a very small angle, it's less than 5 degrees, check it. 0.1 radians. Oh, sorry, tan inverse 0.1. Well, we are not start at, I'm saying 0.1. We cannot start at 0. Multiplied by 180 over this is degrees, you get no radians. Oh, multiplied by 180 over 5 by 60. I told you 5 degrees. It's approximately 5 degrees. So this one you make an error by 5 degrees. So this is start from 0, and it goes to when omega over omega 0 is large. What is tan inverse of large quantity? 90 with a minus sign, minus 90. So the phase angle is minus 90. So it goes from 0 to minus 90. So I take 1 decade less, 1 decade more, so I can start from 0 to minus 90. Okay. Now when omega equal omega 0, minus 45, minus 45. So you know, so you have minus 45, so minus 40. So if I take a line here, now imagine I take a line, just simple line, and I do this. This is the approximation. Let me do it here. So this is the approximation. If I go here and I come to this, so I draw a line, one line. So one line, 1 decade less, 1 decade higher, I draw one line. You see, I'm not making much error, right? The line should go to the minus 45 degrees at the frequency ratio of 1. You don't make much error. Now, after this, it continues 90 degrees, and below this is 0. Below this is 0. So 0 when we are making an error by 5 degrees, right? By 5 degrees. And if you look at what is the log, what is the tan inverse of 10? What is tan inverse of 10? 84 degrees. So we are approximately making again error by 5 degrees, right? Okay. And now when you curve it, when you write from start from 0, go to minus 45 and back to 0 again at one decade frequency higher, you get a fairly accurate plot. Okay. So this is how we do the body plot. Now I have a phase and magnitude, and I have complete information about the system. Okay. So in general, a transfer function may have how many terms, different terms we may deal with. How many terms we can deal with in a general transfer function of high order transfer function. Okay. A constant g of s can be constant, right? G of s equal k, like the amplifier, okay, amplifier, proportion amplifier, right? Okay, and when you write the output of the input is constant. This is the transfer function, zero order transfer function, right? Okay, so this is one. The second one, when we have a zero at the origin. A third case, when we have a pole at the origin. So how many? Three cases. Then when we have a first term, first order term at the as a zero, so we have s plus 5, for example, as a zero. And we have s plus 5 as a pole. So how many we got? 5. And the last, when we have a second order. Any polynomial can be factored into constant s to the power whatever n times a term s to the first order term and second order term. Any transfer function in the world can be composed of this block, right? Example: take a third order polynomial. When we have the characteristic polynomial s cubed plus 5s squared plus 3s plus whatever. Okay. What are the possible combinations? It is one real root and two other real roots, so three real roots, or one real root and two complex. These are the possibilities. We don't have any other possibilities. Yes, okay. So we have either first order terms, constant first order term, pole at the origin, zero at the origin, first order pole, first order zero, second order pole, second order zero, total 7. So we deal with 7 different things. Now in the root plot, in the body plot, now you can do these individually and add them up, stack them up, or you do addition and subtraction. So any complex transfer function can be broken into individual terms that you do the body plot for, and you add these body plots. Okay, you add them. Okay, and you construct your system. And I will take one example like this. So let us look at the g of omega equal k. What is the magnitude here? 20 log k, right? What is it? Constant, correct? Is it function of the frequency? No. So we get constant line over all frequencies, right? So the plot is for this is the one you see there, right? Okay, 20 log k. This is the magnitude. And what is the phase angle? 0. The imaginary part is 0. The imaginary part is 0. So the phase angle, if you have anything you want to bring the class attention to, please speak out. No problem. Don't just talk to your friend. Okay. Now, if I want to plot the Nyquist plot, to plot Nyquist plot, i.e., magnitude, imaginary part versus real part. What is the imaginary part? We have 0. What is the real part? K. So it is a point, right? It is a point. Correct? It's a point. K. The function is K. It's one single point. Right? So this is what we get here. Okay. And the phase angle of it is 0. So it is a real on the real axis. It's a point on the real axis. So let us look at the this term. What we are looking at here, which is a point at the origin, integrator, right? Point at the origin, integrator. So what is the bullet plot for this? Don't look at the board. Look at think. Close your eyes. Think whatever. Do whatever you want. But try to visualize it. 1 over j omega. What is the phase angle? 1 over j omega. What is the phase angle? Minus 90. Minus 90. Right. The real part is 0 here. Okay, so the real part is 0. So this is tan inverse infinity with a minus sign, minus 90, right? So this is minus 90. What is the magnitude? Minus 20 log omega. Minus 20 log omega, right? Minus 20, 1 over log omega, right? 1 over log 1 over omega, it is minus log omega. Minus log omega. So this is simple, right? So you don't need to do anything. So this term now, if I do it, okay, now this is the body plot. The magnitude now here, okay, the corner frequency is omega, omega 0 in this case 1, because omega over omega 0 is 1. Okay, so when omega over omega 0 is 1, what is the magnitude? 0. 0, log 1. Log 1, log 10 to the power 0. 0. Right? Now, if I take 1 decade this, what would be the value? 20 minus 20 log of 0.1. What is log of 0.1? Log 10 to minus 1. Log 10 to minus 1. What is log 10 to minus 1? Minus 20 times minus 1, 20, right? 20. So 20 dB. And here, this value, if it is this, if this one, if I write this one is 0.1 here, so this is 0.1, this one here, 0.1, this would be, what the value, this 20 dB, 20 dB, in dBs, of course. This is 20 in dBs.
So basically the slope is minus 20.
The slope is minus 20.
Per decade.
The slope minus 20, right? No, please leave this alone now. What is if the frequency ratio is 10? 10. So 10 to power 1, right? 10 to power 1. So what would be minus 20? Minus 20. So this is a line basically going over all frequency ratio. It's a line with a constant slope of minus 20, right? Across all frequencies. It's not like K, it's not independent frequency. This is a linear function with a frequency with a slope of minus 20. Going through the crossover frequency is 1. We call this crossover frequency. Crossover is basically the magnitude, and the crossover is 0. Crossover, this is the magnitude crossover. Now, if we look at the Nyquist plot, do we have a real part? No. We have only an imaginary part, right? We have only imaginary part. And so this is how the plot will be. Only along the imaginary axis. Only along the imaginary axis. And the angle is always minus 90. So it is down, minus 90. It should be minus 90 because we measure the phase angle from the real axis. So this is minus 90 up plus 90. Right? Now, if I want to look at a 0 at the origin, How the zero at the origin would look like? Well, anyone? Okay, what you're saying?
Phase angle will be plus 90.
The phase angle will be plus 90. So the phase angle here will be plus 90. Plus 90. Hello? بعثتهم بس بعثيني اياهم بوديهم. ما انا عندي كلاس يا سلوى، عندي كلاس انا اجيبه اذا في هذا باخذهم معي على الغداء كلهم. لا في لا ما خلص انا بس باجي بلحق اشي يخلوا لي اشي يعني. طيب طيب في ناس كثير ولا انا قاعد بسجل طبعا المحاضرة مسجلة. ايوه اذا في حدا يعني باخذهم على الغداء الجماعة معي مش مشكلة، مع عندي بحدود يلا عندي 20 واحد اذا بتغدوهم كويس. يلا ماشي. يلا اللي بده يجي باخذه معي. يلا ماشي اهلين. طيب ماشي شكرا. اهلا. طيب شكرا. Well, I'm chairing this conference, so and I need to come to give a class. Anyway, we had a very nice keynote. I tried to record it, and I will put it, and I give you the link for this. Today we had excellent keynote, and this keynote was related to what you are doing. And basically it was on service robotics, and what the guy was presenting, I want to debate. He was presenting he's coming from University of Twente from Netherlands, and the University of Twente, one of the top universities in Europe. Okay, and he presented basically their work, and three things he focused on. Crawling robots that go into pipelines for inspection and monitoring. Okay, he showed interesting projects, and then he presented an idea, and he was working on low energy and why it is related to your control. Remember, when we want to stabilize something system, we want to add energy dissipation, right? And energy dissipation, because you are wasting energy in friction. Okay, the idea how not to do instead of dissipate energy, store energy for later use. But when you dissipate energy, it's gone, right? So therefore your operation cost will be higher. Okay, so especially if you want to do active damping all the time. So he was talking about design that do not dissipate energy. Okay, that utilize, so you can run, for example, instead of running for 1 hour, you can run for 3-4 hours. Okay, so you dissipate energy, you don't dissipate energy, you store energy for later use. Okay, like degenerative braking, for example. Okay, and he showed basically a jumping robot like Tiger robot. Okay, I don't know if you went to Boston Dynamics. Have you ever gone to Boston Dynamics? Well, I think let me, because I'm doing a review, and I'll post for you a recorded lecture, and I want you have to come on Monday, reading all the recording on your website, or watching the recording, and when I will announce on Sunday that a lecture, online lecture, to finish the preview material. Okay, and to go into the design. So if I go here, just to show you what he was doing. Did you see this?
So can you switch to the projector?
Okay. I showed some of you. They came. They wanted to do. They had, I think, something with Dr. Lotfi. They are doing mechanism. Yeah. Well, I don't know. This is the Boston log, Boston Dynamics log. This is received a lot of funding from the DARPA, from the Department of Defense. They're using it for special operations. Okay? Yeah. And this guy, this consumes a lot of power. Okay, because they're doing, control and a lot of control things that need to dissipate energy all the time to make this stable, etc. And what he presented this guy today is how, instead of doing this, how to use the natural to store this energy for later use. Okay, because when you want to jump to put your leg on the ground again, so you use the stored energy rather than you actuate your motor. Okay.
So it uses the disturbance that you can cause to the robot as stored energy, like you kick the robot.
No, that's this one. It has nothing to do with that. This is a stabilization. Okay. So go visit Boston Dynamics. I know actually the general manager of this used to be the founder of this. Okay, he was. Okay. Okay. Now, what was it? I did not.
The last sentence in the video.
What is it?
No robots were harmed while shooting this video.
Okay. Okay. Now when you talk about when you, I need to stop it here because otherwise I'll keep watching it. Okay. Now when we have now a zero. You see, the zero is exactly the opposite. The zero is exactly the opposite because when you have a zero and a pole at the origin, they cancel out. Now, if you add this, the magnitude plot to the magnitude plot here, it will cancel out zero. And if you add the phase angle from the zero and the phase angle from the pole, they cancel out, right? And this is a pole zero cancellation, correct? You have a pole at the origin, a zero at the origin, they cancel out. Okay, so this is the zero. Now I go to the first order term, and here we the first order term we have a pole at s equal minus 1 over t at s, and let us call this minus omega 0. Okay, now what is the magnitude? This is the magnitude and this is the phase angle, correct? You see that, you see this, right? Okay, now take the log. The log, on the log scale, this is 20 log. Okay, and minus 20 log what? 1 plus omega square t square. Okay, to the power 1/2, right? Or this is minus 10 log 1 plus omega square t square. Okay, that's it. That's it. Now, this is the example I discussed, right? I don't need to discuss it again because we started with this one, right? We started with this one. Now, the Nyquist plot for this, that we separate this into two parts, the real part and the imaginary part. the real part and the imaginary part. If we do this, this is the real part and the imaginary part. This is how they will look. X of omega plus j of y omega, jy of omega, and this will be as follows. Now, okay, so this is the plot here, and we did this last lecture. We did this last lecture. Okay, so you can go over this. And so this is the Nyquist diagram. We are going to focus more on the body plot, and this is the body plot diagram that I have done it before, just today, right? Just today. We did this, right? So we did the minus 20 log and we did the phase angle. These are the asymptotes I drew for you. Okay, and this is 1 over t, this is 1 over t, and this is 0.1 over t, and this is 10 over t. So this is the frequency ratio of 0.1, frequency ratio of 1, frequency ratio of 10. Okay, and you can do it. Actually, I can be good enough to just draw a line connecting the 0 and minus 90 here. And minus 90. This is an approximation. So if you want to evaluate, now you see omega t and the frequency ratio. So if omega t is 0.1, what is the magnitude ratio? Right? And if you take in the log scale, it will be in dBs it will be very small, right? Now in 0.2 you get this one point. So the error in the asymptote is really very small. And this is in dB calculated actually. At 1 it is what is the magnitude? Minus 3 dB. We did calculate this. It's minus 3 dB. When the frequency ratio is 1, correct? It is minus 3 dB. So when omega t from 0.1 to 10, so this is this is how it is. Okay. Now the angle at 0.1 it is minus 6 degrees. At 1 we got it to minus 45, and at 10 you calculated it was minus 84, right? Now, if we have the first order 0, it will be exactly the mirror image. The mirror image. If I put a mirror on the frequency axis, it will be exactly the mirror image. Because the slope instead of minus 20 will be 20, right? And the angle instead of minus 90, it will be plus 90. So it is the mirror image, okay? And okay, and here this is the Nyquist plot. And the Nyquist plot, why it is this way? Because the real part is always, in this case, what is the real part? It's 1. The real part is 1. And the imaginary part is function of omega. So when omega is 0, this is the real, so it is 1. When omega is large, so you get, this is the magnitude basically. This is how it is done. Okay, so this is the Nyquist diagram. So it's not the Nyquist diagram is different from for the pole and the 0. They are different. Okay, now first order system. So if we summarize, this is the first order system. First order pole, and this is first order 0. First order pole, first order 0. And you'll see that this is basically the minor, this is the 1 over t here, okay, the corner frequency minus 45 degrees, and the corner frequency, you see where the asymptotes they meet, this is the corner frequency, this is with the 1 over t, okay, and here you see these plots. You read them? Huh? Asymptotes, right? Yeah. Okay. So let me do one example here. Let me do an example, and now I will do more complex transfer functions. So we did, the only term that we didn't do is are the second order terms. Okay, and the second order terms, it's a little bit more involved, but the concept is the same. There is nothing more, okay. So let me assume that I have G of S. Let me change my color here. I have G of S equal, give me any transfer function.
1 over 3 plus 1 over 3.
Let me take 5 times S plus 1 times over S plus
2 4 1
5. S plus 5, or you want 50? This is S plus 50. Okay. So yeah. Okay. So what I need to do, and let me instead of doing this S plus 5, let me I see erase ink. So let me use this 5. Okay.
So 5 times S plus 5.
Yeah. So this will be, we will first normalize it. This is 5 times 5 times S over 5 plus 1 over S over 1 times 50 times S over 50 plus 1. So now I am having 5 over 5, 25. So this is 0.5 times S over 5 plus 1 over S over 1 times S over 50 plus 1. So now I want to do the both the magnitude and the phase. So I will do a plot for, this is the magnitude plot. This is the 0 dB. Let me start here with 20 dB. Okay, this is minus 20 dB, and maybe here I can do minus 40 dB, and let me use here the 0 angle, the phase. This is the phase plot, and I will use here the 90 degree here. This is 90 degree. This is minus 90 degree, and this is minus 180 degree. I don't need actually the 180, but let me do it. Okay, now let us take the first term. Let me take the 0.5. What is the log of 0.5? 20 log 0.5. Minus 6.02. So this is minus 6.02. So this is here. Okay. I don't have grid to follow. Okay. So this is minus 6. Right? Minus 6.2. You said. Minus 6 is good enough. Okay. Minus 6. Okay. Now let us. What is the phase angle for the minus 6? 0. This is a constant term, so I put blue color here. Now I go to the second term. Which one is the second term? Who wants to do the 0? Who wants to do the 0?
0 and 5.
So if we want to do the 0, okay, Yusuf, you want to do? Okay. So let me first. We need to do a scale. Now, what is the highest? What is the lowest frequency we have? Where is the lowest frequency? And the terms that we have 5, right? We have 5, and we have the highest is 50. Actually, the lowest is 1, The lowest is 1, right? Because S2 over 1. The lowest is 1 and the highest is 50. So I will start from point 1. I will start from point 1. Then this is 10. Then this is 100. Okay, let me... This is 1. Sorry, 1. Yeah, 1. And this is 100. This is 10. I like the 100, so 100. Okay, so this is my frequency grid, right? Now Yusuf, you want to do the first term? Okay. Now where should I? So we go to 5. This is 2. This is 2. This is 3. This is 4. And this is 5. Remember 4. And this is 5 because this is a log scale. 5 is more, quite a bit more than half of the decay. Okay. Now this is 5. This is the corner frequency. So what we do?
Start from -6.
No, let us do it individually, alone. This term alone. So how we do it?
From the 20.
So this is the, we said this is the 5. We need to go to the 50, right? Because we want to see one decade. So this is the 50. So now the high gain slope, this is the 50. I connect the 5 and the 50, and this will be the slope. This is the asymptote, the high frequency asymptote, and this is the low frequency asymptote. Correct?
20 is what?
20 plus, yes, 20 plus. Correct? Do you see this? Now let us go to the phase. So the phase, here the 5, again this is the 5, and this is the 50, and this is the 0.5. This is the 0.5. So what we do in the phase in this case? It is 90. So it is at 50. This is 50. This is 50. It will be 90, right? Plus 90. Sorry, plus 90. So at 50 it will be plus 90. At 0.5 it will be 0. So we draw a line like this. And above this it will be 0, plus 90, and below this it will be 0. So these are the asymptote. These are the asymptote. And now if you do the asymptote, this one, what is the value of the phase at this point? 45. Yes, 45. So this is the phase plot. Is this clear? Now let us ask for someone to do the first poll. You want to do it, right? Yes, you. Yeah, I see you were thinking, even we're talking about the other terms, and you are thinking about this term because I'm going to ask you, right? Okay, so you do it quickly, please. I gave you an easy term. So what is the, and I will do a switch to other color, and let me do this color, okay? So how we do it? You want to help him? Just help him. Just straight line, just straight line. So this is straight line, minus, this is minus 20 dB is slope. So this is straight line, and I go, see, here we said this is the 20 dB, so the minus 20 dB. So this is a straight line across all frequency. So this is a straight line. And what would be the phase angle? Minus 90, yes, minus 90. So the phase angle of this guy will be minus 90. So this is minus 90 across all frequency. There is no real part, right? So this is minus 90. So this is S to minus 1, and this is S to minus 1. Okay, so yes, Abu Ras, yes. 0 till 50. Well, you see, I know you're sleeping, but you are with us. Okay. So this is 50 up to 50. Yes. So then we take the 500. Yeah, this is the 500. This is approximately the 500 frequency ratio, and it goes minus 20 dB. So it goes through this point. This is minus 20 dB, the slope, right? So it goes 0 to 50, and then, yeah, good, very good. What about the phase? So we take the 5 and the 500. So we take the 5 and the 500, and we draw a line 45 at 50 minus 45, and then it continues here. Okay, we did the body plot. We did the body plot. We need to add these terms. We need to add them. Okay, and you want to add them, right? Okay, so add them for us. Yeah, you want to add them. Add them. Yeah, please give me what is how the net plot. I will do it in black. The net plot I will do it in black. Yes. So we go to the low frequency. So add the low frequency. We go to the point 1. We add. Start exactly. Start 20 minus 6. Okay. Normally, the one which is a constant, we leave it. We don't worry about it, and we shift at the end the axis by this much. Well, you see, we are doing.
Okay. We minus everything.
Yeah, exactly. I make the minus 6. I make it 0, and it will be. You see, you add 6 to the whole thing. Okay, or you subtract 6 from the whole thing. Okay, so let us do it first. Let us act not smart and do it this way. So this is we start with this point. So this is 14. We start with 14. So the slope basically will be parallel to this, right? Because we have the same slope until we go actually until we reach 5, exactly, until we reach 5. So we go until we reach 5. And then it is a straight line until 50, right? Then we go down, and this is the net plot. This is the net. This is the magnitude plot. This is the magnitude plot. Now, in the corner frequency, you know that you need to curve the corners only. That's it. You need just to smooth the corner. Put in drawing what you call this a fillet, right? Just put a fillet, right? Just put a nice fillet there, right? To cut the corners, right? And you're done. Okay. Now the phase angle. So minus 90 till 0.5. So this is minus 90, and then it will be. It will be okay. Here it will be minus 45. Okay, and here this will be the same increase up and down. So this will be go to a straight line here to this point, and then it will follow. Okay, now plus 90 minus 90, it will follow this line here. So this is the phase and magnitude plot. This is the phase and magnitude plot. Is this clear? Okay. This is for the constant 4 at the origin, 0 at the origin, first order 4, first order 0. Now we move to the next, what is the time now?
43.
Okay, so I'll need to rush because maybe I'll have a good lunch now after 2 lectures, okay?
It should be 0, right?
Yes, the end should be 0.
Wow, then should be 0. Then should be 0. There is the yellow line and the red line, so minus 90, minus 90. But you have to be smarter here, right? We said we don't want to act smart at this time, but when the frequency is high, at the high frequency, what is G of S at high frequency? It is S over 5 times 0.5 over S times S over 50, right? This is the high speed, the high frequency. So G of S actually approximately for high frequency when omega goes to infinity, it is S over 5. So this is times 50, 10. So this is equal 5 S 1 over S. So 5 times 1 over S, right? So there is a minus 90. There is a minus 90. Okay? Thank you.